Welcome to lecture 19. So in the last class we were trying to state the four functions theorem for distributive lattices. That's what we will start with, and then using that we will see some quick easy applications of the lattice version of the four functions theorem, and then derive a very important and a very popular result known as the FKG inequality, and see a further application of the FKG inequality, further few applications of the FKG inequality. The most important of them would be what is known as the XYZ theorem. Okay, yeah. So FKG are named after three people, whereas XYZ is the reason for XYZ you will see when we reach that theorem. Okay. So remember, I'm not going to recall the four functions theorem in its original version, but I'm going to directly restate it for lattices. Remember that the key ingredient in deriving this theorem from the original four functions theorem was this one-to-one correspondence, or the lattice isomorphism between any finite distributive lattice to the lattice which is formed by the power set of set as under the operation of subset, okay, where the binary relation was the subsethood, right? And the original four functions theorem was stated in the context of the power set of a set with the subset relation. It can be generalized to any finite distributive lattice because of this lattice isomorphism. This is the Birkhoff's representation theorem that we saw in the last class. Okay, so let me state the four functions theorem for lattices. So let L be any finite distributive lattices, and four functions alpha, beta, gamma, delta all are from L to non-negative real numbers. Okay, even though we say plus, it means only non-negative real numbers, and these alpha, beta, gamma, delta satisfy this particular relation for any two elements in L. Okay, remember that in the four functions theorem, this premise was to be satisfied also by any two elements in the power set, or equivalently any two subsets of the domain. And what is the relation? It's alpha x times beta y less than or equal to gamma of x join y times delta of x meets y. Okay. Now remember, in the normal four functions theorem, the original four functions theorem, this was the union and this was the intersection of alpha, beta. Though they were since they were elements of the power set, they were actually sets, and hence under the lattice isomorphism, under the lattice isomorphism from L to the power set, it is the join operator which gets mapped to the union, and the meet operator which gets mapped to the intersection. Okay, so this is in accordance with the four functions theorem, and hence the conclusion of the four functions theorem will also hold, which is the same inequality remains true even if you overload these alpha, beta, gamma, delta to act on collection of points on the lattices instead of single points, with this join and the meet operator replaced with the appropriate pairwise join and pairwise meet operator for the collections. Okay, so that's what this line says, and you would have guessed what was the set pairwise join operation and the pairwise meet operation. I'm just stating that for completeness. Okay, so yeah, the pairwise join operator of two sets is you go inside the two sets and collect every element from the first set and every element from the second set and take their join. This collection is the pairwise join. Similarly, the pairwise meet is also x meet y for every x in x and every y in y. The pairwise join and pairwise meet respectively take the role of pairwise union and pairwise intersection in the original version of the four functions theorem. Okay, so the original version of the four functions theorem is actually embedded here. But this is in certain contexts where the underlying structure is obviously a lattice structure. This is more directly applicable. Okay, and this is just the definition of the overloading. phi is any of this alpha, beta, gamma, delta, and phi is actually a function from L to R plus, but we are going to overload it and also treat it as a function from subsets of L, 2 power L to R plus via this sum operation. Okay, we're just adding up all the guys. And proof I'm not going to say in detail, but you should verify that this is once you prove the four functions theorem and the Birkhoff's representation theorem, this is immediate. Okay, this is just you take the lattice isomorphism from this lattice to the power set and write the four functions theorem for that power set, and it will give you the four functions theorem for these lattices. Okay, so first let's see a couple of easy or quick applications of this theorem. Let L be any finite distributive lattice. So from now on, I will abbreviate this finite distributive lattice as FDL. Let L be any FDL and X and Y be subsets of L. Okay, so X and Y are just two subsets of a lattice, and we can show that their product of their cardinalities is upper bounded by product of the cardinality of the pairwise join times cardinality of the pairwise. Okay, so proof is almost just a single line. You take your alpha, beta, gamma, delta to be the constant function. Okay, it is 1 everywhere. Okay, so alpha, beta, gamma, delta is constant everywhere. Okay, so yes, it's a function from the lattice to the non-negative real numbers. In fact, it's a function where the codomain can even be reduced to a singleton set. And does it satisfy the premise? You have to check that for all two members X and Y in L, this relation alpha X beta Y is at most gamma X join Y delta X meet Y is satisfied, but which is obvious, it is true, because for every X alpha is 1, for every Y beta is 1, for every thing inside gamma is 1, for everything inside delta is 1. So this is just checking 1 less than or equal to 1. So the premise is easily satisfied, and hence the conclusion of the four functions theorem for lattices follows, which is exactly what is written here. Cardinality of X is just alpha of X, because alpha is the constant function on the lattice. So when you overload this function and apply it on sets, it essentially counts the cardinality of that set. So this alpha of X is cardinality of X. Similarly, the others also, right? Beta of Y is the cardinality of Y. Gamma of X pairwise join Y is the cardinality of X pairwise join Y, and so on. Direct application. This is a very quick application, but this is an interesting result. Okay, even if this was restricted to just L being the 2 power n, L being the power set of some ground set n, this is still interesting. Remember, so yeah, this is the case that I have mentioned here. Think about the case when L is 2 power n and the relation is subsethood. Okay, so we know that if this family X and Y have cardinalities M and N each, when we define this pairwise intersection or pairwise union, we remark that the size of the pairwise intersection of two families can be as large as Mn, because there are M options to pick your first set from in the intersection from, or in the union in this case from, and N options to pick Y from. So this could be as large as Mn. We only knew that both the pairwise intersection as well as the pairwise union had at most Mn elements, but it could be smaller. There could be a lot of collapse because some x1 union y1 may be equal to some x2 union y2, in which case they do not give you two different sets in the pairwise union, but they collapse into one. So yeah, it's much smaller. Like for example, consider this case where X is all the subsets of the first n by 2 elements, and Y is the family which consists of all the subsets of the upper half elements. Okay, so no set in X has an intersection, as a non-empty intersection with a set in Y. If you take any set from this family X and any set from this family Y and take its intersection, the result is going to be an empty set, which means the X pairwise intersection Y. Here I'm using the pairwise meet notation, but in this particular lattice, the pairwise meet is nothing but the pairwise intersection. Okay, so X pairwise intersection Y is just contains the empty set phi. So its cardinality is 1. Remember, we only knew it could be as the upper bound was Mn, but it could be as low as 1. Okay, interesting. But in this case, from this inequality, from this result here, since the product of these two has to be equal to, remember what was the cardinality of x in this case? It was all subsets of some n by 2 elements. So this is 2 power n by 2. This is also similarly 2 power n by 2. Product of their cardinalities therefore is 2 power n by 2 plus n by 2, 2 power n. So left hand side here is 2 power n, and hence the right hand side has to be greater than or equal to 2 power n. This is only 1, which means this has to be greater than or equal. In fact, cannot be more than 2 power n, because this is also is also a subset of the power set. Okay, so in this case this is 2 power n. Okay, but for this particular example, it is not difficult to verify that even directly. You can see that any subset of n can be created by picking one set from capital X and one set from capital Y and taking their union. Now there is also, you can also verify that if you take this this entry wise complement. Okay, this is not the complement of the family. This X double bar denotes you enter inside X, take every set S from this family and take its complement under the ground set that is given to you. So this is X double bar. So if you take the element wise complement of this family and this family, then you will see that the opposite is true. Okay, your pairwise union only contains a singleton set, which is a universal set, and hence the pairwise intersection should contain all the elements in the power set. Okay, so yeah, these are interesting things. Or you can even try the case when X and Y are downsets. When X and Y are downsets, you know that the pairwise intersection is not big, right? The pairwise intersection is just X intersection Y, which means your pairwise union has to be large. Okay, because pairwise intersection, since it's just a family intersection, its size is at most the size of the smaller family. So it's min of m and n, which means their pairwise union should be at least the size of the larger one. Okay, mn by min mn and so on. So there are lot of things which kind of just follow from this inequality here. Okay, so yeah, it's a useful inequality to know. Now the next, again a quick application is the following. You take any family of subsets. Okay, here we are directly talking about family of subsets. Remember the application one, though the examples that we saw was about family of subsets, it applies to any two lattices in general. But here this we will only apply to family of subsets of n. Script A is such a family. Then the difference set of that family, or the difference family of A, is you take any two sets from this family and take their set difference. Okay, so it's A minus B, where both A and B come from the family. This is called the difference set. And then what this result says is that the difference family has at least as many sets as the original family. Okay, the cardinality of D of A is greater than or equal to cardinality of A. This is again a easy application, but a clever application of the four functions theorem. Take your, or in fact we will actually just apply this application 1. So we will prove this as an application of application 1. So we have to construct this X and Y appropriately. Okay, so yeah, what is your X? I'll take my X to be the script A itself and Y to be the element wise complement of script A. We already defined that, but this is what it means, right? You go inside, pick every set from this family and then take its complement under the universal set. Okay, take its complement under the universal set. Now from the previous application we know that product of this is true, right? And okay, this time I replace the pairwise join with the pairwise union and so on, but yeah, since we are in the power set case, it's the same. Now what would be cardinality of X? The first term here, it would be, just because X is the family A, it is cardinality of A. Cardinality of Y, also a minute's thought will convince you that it is same as cardinality of A, because this pairwise complement has exactly the same number of, this pointwise complement has exactly the same number of elements as the original family, right? For every set in the family X, you get exactly one set in the family A double bar, and there will be no collision, because if the complements of two sets have to be the same, then the original sets also have to be the same. So there is no collision occurring because of this operator, or more formally you can argue that the function which maps a set to the complement of its set is a bijection inside of this 2 power. Okay, so if you have a bijection between, so this is a bijection between is a bijection from script A to script A double bar. Okay, so if you have a bijective function between two finite sets, they have the same cardinality. Okay, so why is that? Now, what about the cardinality of the pairwise intersection of x and y? Okay, so yeah, by definition, what is a pairwise intersection? A intersection B, where A is from the first family, B is from the second family. The second family, remember, here is the A double bar. But now, if B is in A double bar, that means it is complement of a set in A, right? So B is the complement of some A prime, where A prime is in A. That's what we have written here. But now A intersection, the complement of a set, is nothing but A difference that set, right? Think of A and A prime. A intersection, the complement of A intersection, the complement of A. So you cannot include anything in A, which is this portion, which is equal to, this is your A intersection A bar complement, which is nothing but A minus A bar. So this is the definition. This fits the definition of the difference set. Okay, so your X pairwise intersection Y, or in particular script A pairwise intersection script A double bar, turns out to be the difference set. Okay, so this is D of A, and hence its cardinality is cardinality of the difference set. The most interesting part of this calculation is the how do we model the X pairwise union Y. So this is by definition A union B, where A comes from script A and B comes from script A double bar. But again, as before, if B is from script A double bar, it's a complement of some A prime, where A prime comes from A. But now this time it is the union of two guys, right? A union A prime bar. Okay, so this contains this because it contains A. Now it does not contain A prime, it contains A prime bar. Okay, so since it contains A prime bar, it contains the rest of this, right? Now this is nothing but A prime minus A, the whole is complement, right? So oh, by the way, I think the blue shading was not correct. The blue shading should have included it's not an intersection, it's entire A. So what is left out, which I'll maybe shade in red, is this area, which is nothing but A prime minus A. Okay, so this guy here is nothing but A prime minus A's complement. Okay, but so this is not equal to the difference set, but this is the point-wise complement of the difference set. So if you enter your difference set, you will see guys like A prime minus A, and if you take its complement, what you get is the point-wise complement of D of A. But then they have the same cardinality, right? Because it's point-wise complement and the original family has the same cardinality. So cardinality of X pairwise union Y is also cardinality of D of A. Now you substitute all of them into the this inequality, which is application 1. You will see that cardinality of A squared is less than or equal to cardinality of DA squared. Everything are positive numbers, so you get what you want. Okay. Now the most one of the probably this is FKG inequality. I mean, it sits between the Clyde-Benz inequality and the four functions theorem, but this is for some reason the most popular among these correlation inequalities. Maybe though it is not as general as the four functions theorem, maybe it is easier to apply in a lot of contexts, especially in statistical physics. Okay, so outside of combinatorics, this was discovered outside of combinatorics. In fact, this was discovered by physicists in the context of statistical physics. Okay, and it is widely used. In fact, Wikipedia says that this is a fundamental theorem in statistical physics and probabilistic combinatorics. So this is named after the three people who discovered this, Fortune, Castellin, and Ginibre. Okay, I'm sure I'm pronouncing them wrong. Okay, so don't take me for the for the pronunciation of these words. It's a theorem from 1971. To state this theorem, the proof will be almost immediate from the four functions theorem, and this is on lattices. But in order to state that, we need to define a special type of function which we call the log supermodular function. Okay, so what is a log supermodular function? This is a function from a lattice to the non-negative real numbers. Okay, so we are only treating such functions. So let mu be a function from a lattice L, and in fact we will restrict ourselves. This definition applies to any lattice. Yeah, I could have said this applies to any lattice. Why kind of reduce definition. Okay, so a function from a lattice to non-negative real numbers is called log supermodular if for every pair of elements in the lattice x and y, mu x, mu y. Now look, there is this relation here looks like the premise of the four functions theorem, but instead of four different functions, you are talking about the same function mu taking the role of alpha, beta, gamma and delta. So if you have already, if your memory already has the premise of the four functions theorem for lattices, this is exactly that, with mu taking the role of all the four, alpha, beta and gamma. Okay, but why is this called log supermodular? So if you take the log on both sides, you will see that log of mu x plus log of mu y is less than or equal to log of mu of this x join y plus log of mu of x meet y. So two functions, if log of this mu I treat as another function, to a function which satisfies this kind of an inequality with addition replaced by multiplication is what is known as supermodular, and hence this is called log supermodular because somebody defined or used the word supermodular first. That's why this has to be satisfied with such a long name. Now, two quick reminder definitions, but these are things which are probably much easier than this log supermodular. A function again from a lattice to, by the way, this I can define for any partial order, not just lattice, but okay, let me, in the interest of time, just let me limit the definition to lattices. Okay, so a function from a lattice to, again, non-negative real numbers. Here also you don't need the non-negative real number. Okay, so actually you can define this from any poset P to R. Okay, it is called an increasing function if x precedes y in the partial order, then fx should be less than or equal to fy. Okay, so remember, there is no strict condition. This is not the strictly increasing definition. It is okay if, for example, even the constant function fits the definition of being increasing. Okay, so even if x precedes y and x not equal to y, it's not necessary that fx should be strictly less than fy. It's okay for fx to be equal to fy. Okay, so this is in some sense the more appropriate name should have been non-decreasing, but again we already have a long name up here, so let's not have another one here. Increasing would just mean this weakly increasing. Similarly, decreasing would mean for if x precedes y, then fx greater than or equal to fy. These are the three terminologies that we will need to state the four functions theorem. This increasing, decreasing is very natural. This log supermodular, if you are seeing it for the first time, then please pay attention to this condition. Now, the FKG inequality states the following. Let L be any finite distributive lattice. It's important that it is finite and distributive. Okay, let L be any finite distributive lattice. Mu is a log supermodular function from the lattice to non-negative real numbers, and f and g, let's say, are both increasing functions from this lattice to non-negative real numbers. Okay, so L is a FDL, finite distributive lattice. Mu is log supermodular. F and g are increasing. Then this is the conclusion of the FKG inequality. I know it looks extremely lengthy formula. We will state a compact version of this formula soon enough, but currently try to interpret this. Okay, so this is in some sense the function mu f extended setwise but applied on the whole family. Okay, so most of the time we will use mu x to kind of filter the application of fx to some subset. So if you only want fx to fg etc. to apply on certain subsets, we will use mu to get that effect. Okay, maybe I'm jumping guns here. Okay, currently this is what it says. Okay, your weighted average of by weighted I will always mean weighted by mu. So your weighted average of f in the whole of L times the weighted average of g is upper bounded by the weighted average of the function fg times the total weighting. Okay, so most of the time it is at least to remember this, it is convenient to normalize this mu. But yeah, before stating the compact version, because the proof essentially gives you this version, let's first see the proof. It's a very direct application of the four functions theorem for lattices, and many of you, in fact, if you haven't guessed it already, you should try that and guess it now. Given this mu, f and g, what would be your alpha, beta, gamma and delta? Okay, just that much is there in the proof of this result. So I'll prove and then come back and restate this in a more compact and easy to remember form. So your alpha is nothing but mu times f, beta is mu times g. So then what does this boil down to? This boils down to sigma x element of L, alpha of x, which is nothing but alpha of the entire lattice, because alpha we know is overloaded that way. To apply it to a set, it automatically takes the sum of the values that it assigns to each member of the set. So this thing in the entire brackets then becomes alpha of L, and since your beta is mu g, or beta of x is equal to mu x gx for all x, this becomes beta of L. What is gamma defined to be? Gamma is defined to be mu fg, and delta is just defined to be the single mu. So this becomes gamma of L, and this becomes delta of L. Okay, and now you see that this is really the conclusion of the four functions theorem. The conclusion applies to any family script A and script B for this L and this L, right? But we can also apply it to script A being the whole lattice and script B being the whole lattice, and this should have been the pairwise join with B, but since A and B are both the entire lattice, their pairwise join is also the entire lattice. You can, maybe if you're confused here, you can even verify that any member of the lattice can be written as a join of that element with itself, right? X is equal to x or x. So this tells you that every x, since your the family is the whole of x, the pairwise join is also the whole of x. Similarly, the pairwise meet is also the entire x. Again, you can write any x as x meet x. Okay, so this is just the conclusion of the four functions theorem applied on the whole lattice. But we have to verify the premise. Okay, but what is the premise? The premise is for any two members of L. And what do you have to show for any two members of L? You have to show that alpha x beta x is less than or equal to gamma x join y delta x meet y. But let's see what is alpha x. Alpha x is just mu x fx, beta y is mu y gy by definition of alpha and beta given here. So if I rearrange them, it's just using commutativity here, mu x mu y times fx gy. But now for mu x mu y, I can use the fact that mu is not any function, it's a log supermodular function. Hence your mu x mu y is upper bounded by mu of x join y, mu of x meet y. Okay, so this uses the log supermodularity of this. Okay, and that is why you have a less than or equal to here. Okay, now next, your f and g we know are increasing functions, right? So x or x join y is something which is always succeeds both x as well as y. Okay, x precedes x or y, so f of x has to be less than or equal to x or y, f of x or y, because f is increasing and x precedes x or y. Similarly, if you consider this g of y precedes x or y and g is increasing. So g of y will be less than or equal to g of xy. Okay, so we have used the fact that f and g are increasing at this stage. And now everything is clear, right? Now you group the first three terms together and so not the first three terms, you group your mu of all the terms which contains x join y together. You will get this, which is nothing but the gamma of x join y, right? Because that's how gamma is defined, right? That's how gamma is defined. And this last term, which is on the x meet y, is exactly the definition, delta. Okay, so you get this, putting it all together, you see that alpha x times beta y is upper bounded by gamma x join y delta x meet y, and hence this satisfies the premise of the four functions theorem for lattices, and hence the conclusion follows. And the conclusion we can apply for the entire lattice, and that's exactly what is the FKG inequality. Okay, so this is done. Now let's see how to remember the FKG inequality, because this is there's a bit, how do you say, a mouthful to remember, right? So why did I do that? Let's interpret this in terms of probabilities and expectation. So the first trick is something which we already hinted. We will normalize mu by dividing it by mu of L, so that mu looks like a probability measure. Okay, so whatever is the mu that is given to you, right? What is mu of L? Mu of L is nothing but sigma x element of L, mu of L, right? And then I'll define this mu prime to be mu prime of any x to be mu of x divided by mu of L. Okay, now in order to again avoid carrying this primed notation throughout, instead of doing this normalization, I'll assume that the mu that is given to you is normalized, or we will assume that this is equivalent to assuming that mu of L is equal to 1, mu of the entire lattice. That is, if you sum mu over the entire lattice, you will get 1. You can get this by a normalization, since mu always appears in the same degree on either side of the inequality. This does not change anything. Okay, but once you assume that mu is now mu satisfies all the requirements for a probability measure, right? Why? Because once you do that, mu is a function from the lattice. Originally it was to all positive real numbers, but now it is to the interval, closed interval 0, 1. Moreover, each if you sum up mu, it results in 1. This is all the requirements of a probability mass function. Okay, its range has to be in 0, 1, and if you add up everything, you should get 1. So it satisfies the definition of a probability measure. But then remember, a common, a likely mistake you can make is that you might forget the important condition. Not every probability measure will satisfy FKG. It will only be satisfied, FKG will only be satisfied by log supermodular probability measure. Okay, so mu has to be a log supermodular probability measure. Okay, so it's a probability measure which satisfies the condition that mu of x for all pairs x and y, mu of xy less than or equal to mu of x join y, x meet y. Okay, so if it is such a probability measure, and f and g, I am not changing anything, they are just increasing functions. This whole FKG inequality is essentially saying that the expectation under this probability measure mu of the product function fg is greater than or equal to the product of the expectation. So this can be remembered as f and g are positively correlated. Remember the Kleitman's inequality, after we stated the combinatorial version, we converted it into a probabilistic language and said that this is equivalent to saying that two events are positively dependent. Similarly, this is equivalent to saying that two functions are positively correlated. Okay, you say that two functions are positively correlated if the expectation of their product exceeds the product of their expectation. In fact, they would be independent, if this product expectation of their product could be decomposed as equal to the product of their expectation. Similarly, if it was the inequality was in the other direction, we will say f and g are negatively correlated. But why is this true? You can verify this term by term, By the way, remember I wrote in the easy to remember form, I kind of reversed this whole inequality and I wrote that this guy is greater than or equal to the product of these guys. Okay, so let's verify it term by term. This is easily seen to be the expectation of the random variable f, right? If L is your sample space, and your f and g are random variables, then this is the expectation of this. Okay, now I can call this the expectation of f, but under this probability measure mu. Similarly, this is the expectation of g under the probability measure mu. What is this? This is again the expectation of fg. Okay, because you are taking the weighted average of fg again under the expectation, under the probability measure mu, and this is nothing but 1. That is our assumption. Okay, so now if I just reverse the inequality, I get this form. Yeah, this says that the functions f and g are positively correlated, but do not forget the conditions. This applies to a finite distributive lattice. Mu has to be a log supermodular probability measure, and f and g have to be increasing functions to non-negative real numbers. Okay, so yeah, as an exercise, you can show that if f and g were both decreasing functions, but again to, let's say, non-negative real numbers, then the same inequality will hold, the positive correlation will hold, whereas if f is increasing and g is decreasing or vice versa, then they will be negatively correlated, which means the sign of the direction of this inequality will be reversed. But this is an exercise. Okay, and I also wanted to state that this requirement that f and g that its domain has to be non-negative real numbers is not serious once we reach the FKG stage. Okay, for all the 4 functions theorem and all, it's very important, because if you remember, the proof was very geometric, right? The rectangle sides were alpha 0, alpha 1, etc. But with the FKG inequality, you can extend it to f and g being functions from a lattice to any real numbers. Okay, you can extend the codomain to the entire R. How do we do that? Again, remember that L is finite, so you can find the minimum value of f and the minimum value of g. Let's say f and g when negative, right? This is your f, and say this is your g, but this is a finite function. It's a function on a finite domain. So you find the point where they are at their lowest most, and among the two, you take this lowest guy and call that as minus k, or this gap is what you will call as k. Okay, or more formally, what is k? K is the minus the minimum of f meet g, which again is taking the minimum of f and g and then finding its lowest point, and then the distance to 0 from that point is your k. Well, this is easy. All I'm trying to do is that I'm saying that I can add a constant to f as well as g to make them functions to r plus. Okay, if I, instead of considering f and g, I can consider f plus k and g plus k. So even if f is not to r plus, this f plus k of x is always greater than or equal to 0, and g plus k of x is always greater than or equal to 0. So they will satisfy the requirements for the FKG inequality. But then what is the correlation? What is the expectation of the product? I am hiding the mu because I don't want to write this mu every time. I am hiding that. This is, you multiply it inside and use linearity of expectation. You will get this EFG plus k times E of f. That's where the linearity of expectation comes in, and k times E of g, plus this is a constant, so that stays here. And since these functions satisfy the claim, I'm now looking at the other side of the FKG inequality, which is the product of the expectations. Now, this again, you use the linearity of expectation. This becomes EF plus, this is just a constant, so it's k, EG plus a constant, that's a k. So you get EF, EG plus these guys. Now, if you look at this equation and this equation closely, you will see that the last 3 terms are the same. It's only a relation between the first 2 terms. And these 2 guys, we know, are positively correlated. F plus k and g plus k are positively correlated under supposing mu is log supermodular and f and g are increasing. So this relation essentially now boils down to only the relation between the first 2 terms. Okay, so EFG is greater than or equal to EFEG. So Yeah, so what is the summary? So I can even remove this if it is needed. So if but yeah, let me write it down because that's the way I have proved it, and maybe I'll be sharing these notes. So on a finite distributive lattice, if you have a log supermodular probability function, then any two increasing functions of the lattice are positively correlated. Okay, and from that you can easily derive the other corollaries. Okay, so it looks like I won't be able to prove the XYZ theorem in this class, right? But so let me stop after giving you this exercise. So using FKG inequality, try to prove the non-uniform Kleitman's theorem, right? The proof is actually very simple. You only have to define mu in the way that you want this non-uniform probability measure. But this way of picking each element with a probability that depends on that element. But the key fact here is that you are constructing this set as, again, the coin tosses at each point which decides whether that point is in your set or not should be independent. Only then this product formula is valid. If you then, this is the probability that you will get. First, in order to prove FKG, prove this non-uniform Kleitman from FKG, it is actually just enough to verify that this is log supermodular. But check that and then complete the proof by writing in the details which will give you the non-uniform Kleitman's version. You can then compare it with the proof of non-uniform Kleitman's version from the four functions theorem. In some generality they are the same, but you will see that you need to be quite clever to have guessed the proof of non-uniform Kleitman from the four functions theorem. For some reason, maybe because there is already a notion of probability measure that is in the FKG inequality, this using FKG to prove this non-uniform Kleitman seems to be more natural than using the four functions theorem. Okay, so we will wind up for now and we will postpone this XYZ theorem for the next lecture. Thank you.